All right, it looks like a bunch of people hopped back on, which is great. So we're going to get started. So welcome to our quarterly number 2 live stream review. This is mostly a Unit 3 test, right? There's not much that we've done this quarter that was not Unit 3 other than being able to work with quadratics and being able to do some function analysis. So we'll talk a little bit about that. If you're in my classes, feel free to shoot me a reminder anytime live. If you're not in my class and you want to send me a question while we're live streaming, there's a remind link on the screen that you can just sign up for that. I won't send you messages. It's just so you guys can message me. The other thing is if you're watching this on a replay or watching it later, the blank copy of this document is on OneNote. So if you guys go to my OneNote and you want to print that out, that is a way for you to sort of practice along with me. So feel free to do that, okay? So the first thing that I want to point out to you guys and I want you to remember as my screen flips around is that you guys have learning targets, right? So on your unit overview, if you're in my class, or I think most of your other teachers are doing this too, you have a unit overview that has learning targets on it. It's where we do our warm-ups in my class. So this has a list of all the things you need to be able to do, and you can use this to check off as you study. So I can add, subtract, multiply, and factor. I can do that. I can prove algebraic identities. I can do that, right? And as you're studying, you can go through and make sure that you know everything you need to do. The one thing that I would say for our purposes in Regents is we are not going to talk much about these bottom two. These are things that are not part of our curriculum, specifically in what we've covered so far, and we'll come back to them later in the year. So don't fret if you're studying and that looks like something that doesn't look familiar. So, some basic vocab before we get started, just to make sure that we're all on the same page here. So, first of all, when I talk about standard form tonight, what I'm talking about is being in order from biggest to smallest exponent. So, for example, if I have something like 2x to the 5th minus 3x to the 4th plus x squared minus 7, right? I'm looking at the exponent of my variable, of my x term, and I'm putting those in descending order. So that's what I mean when I say standard form. The other two things we'll talk about a bunch are the degree and the leading coefficient. The degree is the highest exponent when we talk about it being in standard form. So for instance, in the polynomial that I have as my example up here, my degree here would be 5 because that's my highest exponent. Now, if it's in factored form, you'll have to think a little bit more about what the degree would be because it's not already in standard form. The leading coefficient is the coefficient of the term with the highest exponent. So you need to make sure that it's in standard form before you make that decision. So that's just something I would keep in mind to think about because people tend to goof on figuring out what their leading is. So the first thing we talked about in this unit was polynomial identities, and this was 3.1. This was looking at statements that are always true. So an equation that is true for every value is called an identity. I always think about like your identity is looking in a mirror, and so an equal sign should almost act as a mirror. The left side and the right side should be the same. If we want to show that something is an identity, we start with either side and show that it can be changed into the other side, okay? Or you can work on both sides separately, but you cannot cross the equal sign. Here's the other thing that I would say is really, really important. Proving something is true for one value is not proving it for all values. So you don't want to just plug in a value and say, look, I proved it. You've only proved it for one number, not for every number. So you need to be careful with that. So if you got a question like this, verify that this is an identity for all values of x and y. What I'm really going to do is sort of treat the left side and the right side separately. And my goal is going to get them to look the same. So on the left side, I have x squared plus y squared. And squaring, remember, means multiply it by itself. So you can either use double distribution or you can use a table to multiply these. I'm going to do this with double distribution because we'll do a lot more later in the live stream with the table. So x squared times x squared would be x to the 4th. X squared times y squared is x squared y squared. Same for those. And when I write those, I actually am going to write them in the same order because it helps me to remember that they're like terms. And then y squared times y squared is y to the 4th. So on the left side, I get x to the 4th plus 2x squared y squared plus y to the 4th. So I know that's my left side. Now on my right side, let's do same thing. Let's kind of do the algebra that we can. So I'm going to write this out twice, right? And I'm going to multiply these. So x to the fourth minus x squared y squared minus x squared y squared plus y to the fourth, because we're doing a negative times a negative, right? And then for this one, I'm doing 2xy all squared. So I need to square each part. So plus 4x squared y squared. Now I've got some like terms here. I can combine all my x squared y squared. So -1, -1, and 4, which gives me positive 2x squared y squared. And now what I've shown is that my left side and my right side are equal. So when you're proving an identity, that's what you're looking to do. You're looking to algebraically show that your left side and your right side come out the same. All right, I'm going to go on to other stuff. If you guys have questions, send them to me. I'm happy to answer them, but this is a topic we were pretty strong at least in my class, so I'm not going to spend tons and tons of time on that. Okay, let's look at division. And again, this is another thing that generally we've been pretty strong at least in my class. There are 2 different methods you can use for division. I have no preference as to which one you use. You can use reverse tabular or long division, but make sure that you have mastered one method. I don't care which one you master, but make sure you've mastered one. If you like long division, make sure that you remember to put in zeros for any missing factors, right? So if you have a missing term, missing terms. If you have a missing term, you want to make sure you put a 0 in for that, and we'll talk about that in a second. So I'm going to do the first one with the reverse tabular. The second one I will do with long division. So we've got a little rundown of those. But again, if you have questions as I'm doing this, shoot them to me and I'm happy to answer them. So I'm going to, on the first one, divide 3x to the fourth plus x cubed minus 2x squared plus 4x minus 2 by x minus 2. And the thing that I want you to remember here is when you're setting up your reverse tabular, you're basically undoing multiplication, right? So normally when you multiply, your 2 factors go here and here, and then the answer goes in, or the product goes inside the box. Division, we're undoing that. So x minus 2 will go over here. And when you divide, you're actually finding the missing factor. So what's up there will be my quotient. What's in the box are the terms that will combine to give you the original. So if this is going to multiply to be 3x to the fourth, then I need to think x times what would give me 3x to the fourth. That would be 3x cubed. And then you can fill in this box down here by multiplying just like you're doing, the box method to multiply. So that would be negative 6x cubed. Now from there, you have to say, okay, I know that there's positive 1x cubed in this. So along this diagonal, these need to combine to equal positive 1. So this is going to be 7x cubed. And then you can say, okay, well, x times what would give me that? So that would be positive 7x squared. Then you can multiply minus 14x squared. Now again, we know along this diagonal, they need to multiply to be, or add to be my x squareds. So I need to have negative 2x squared. So I'm going to add 12x squared to that, right? And that's going to be plus 12x here, because 12x times x would give you 12x squared. And this would be negative 24x, right? From there, we know that these 2 need to combine to give me positive 4x. So I know that that's going to wind up being 28x. So that's plus 28. This is going to be minus 56. And I know those need to combine to be negative 2. So that's going to be plus 54. Now, I can't have x times something that's not a fraction to give me 64 or 54, I'm sorry. So this is my quotient, 3x cubed plus 7x squared plus 12x plus 28. And then I have a remainder of 54. So that's going to be plus 54 over what we divided by, which was x minus 2. Now again, you could do that with long division. You would get the same answer. It would just be different steps. So this next one I'm going to do with long division for those of you that like this better. And I want to do this with long division because we need to be very particular about this. So this says to divide this by x plus 2. And the first thing that I noticed there is that I have a missing term. So I've got an x cubed, but I have no x squareds. I have an x to the first, and I have a minus 1. So I'm going to need to fill in that missing term when I do the long division. So dividing this, it's going to be x cubed, 0x squared, plus x minus 1, and the x plus 2 will go on the outside. Now when I do this, I start by saying, okay, x times what would give me x cubed? That would be x squared. And then you're going to multiply this x squared times this whole expression on the outside there. So it's going to be x squared times x, which is x cubed, and x squared times 2, which is 2x squared, and that's positive. But remember, we need to subtract these, so I put those in parentheses and subtract them. X squared minus x squared cancels out. 0 minus 2x squared is negative 2x squared. Then I'm going to bring down my next term. Now we're going to repeat this process, and I'm going to use a different color here. So x times what would give me negative 2x squared, and x times negative 2x would give me negative 2x squared, right? So this would be negative 2x squared, and then negative 2x times 2 would be negative 4x. Remember that we're subtracting those, so I'm putting that in parentheses. Negative 2x squared minus negative 2 cancels out. X minus negative 4x is going to be 5x. Make sure you're subtracting a negative, and then bring down your negative 1. And then let me shrink this down a little bit so it fits on our screen. We're going to repeat this again one last time. So I would say x times what would give me 5x? That would be plus 5, positive 5, right? So this would be 5x and then plus 10. I'm going to subtract those. 5x minus 5x is 0. Negative 1 minus 10 is negative 11. So my remainder is negative 11 over x. Or my remainder is negative 11, but I would write it as negative 11 over x plus 2. Okay. Any questions on division before we go on, please send to me. Again, I don't care which method that you like better. Choose one, go with it. Just make sure you are really a master of it. And if you're doing long division, remember that you need to put in zeros for any missing terms. And also remember that you're doing subtraction at every step. So remember to distribute out your negative. Okay. So remainder theorem. This is one that can easily be forgotten, but really we need to be able to apply this to the factor theorem. So for the remainder theorem, here's what it says. The remainder when p of x is divided by x minus a is going to be equivalent to p of a. So in other words, we would take the factor we're dividing by, we would find the 0 of that, right? Set that equal to 0. And then we can plug that into our function, and that will equal the remainder. So that's the basic idea. So this is the way they've asked it on the Regents before. They'll say, what is the remainder when p of x is divided by a given expression? And this is p of x in my picture. So I'm dividing p of x by x plus 2. Notice I do not have a formula for p of x, right? So what I'm going to do instead is say, okay, the 0 of that is negative 2, right? And I'm going to find the remainder by evaluating p of negative 2. So p of negative 2, look at your graph. At negative 2, this equals 4. So the remainder would be 4. And an important question you might have there as well is that a factor. Notice you have a remainder that's not 0, and so x plus 2 would not be a factor, right? Same thing if you had x minus 3. We'd look at the 0 of that, which is at x equals 3, and then we would find p of 3. And so looking at my picture, at 3, the value is 0. That means that the remainder would be 0. And that should tell you, hey, this is a factor, right? And think about it. We know that if 3 is a 0, then x minus 3 is a factor. So we start to connect all of this stuff that we've done. Okay, So that leads us right into the factor theorem. So that's basically what we were just doing. We're just kind of extending it out a little bit more. So you will often get a question like this. So given p of x equals this, find k if x plus 3 is a factor. So I would start with this. If you know x plus 3 is a factor, then you know that the remainder equals 0, right? And x plus 3 means I'm looking at when x is negative 3. Now you could do division here. It's just going to be a lot more work. So what I would say is let's use the remainder theorem. Let's say, okay, we know the remainder should be 0. That means we know p of negative 3 should equal 0. So I'm going to plug in 0 for x plus 3 times negative 3 squared plus k times negative 3 minus 6. And I know that that should come out to be 0. So let's see where that gets us. So 0 equals, this expression right here is negative 54. Yep. This right here is positive 27. This is negative 3k, and that's minus 6. So then I get 0 equals, let's see, these combine to be negative 27 minus 6 is negative 33. So I get 33 equals negative 3k. So k equals negative 11. Now again, you could do that with division and really work backwards. That's a lot harder than just knowing the remainder theorem or the factor theorem and knowing that your remainder has to be 0. So same thing for this one, which binomial is a factor. You are welcome here to divide 4 times, but that's a lot of work. So what we could do instead is we could say, okay, what are the zeros that we associate with these factors, right? So this would be x equals 2. This would be x equals negative 2. This would be x equals 4. This would be x equals negative 4. And then what we could do is plug those each into this. If it's a factor, we know that that should come out to equal 0. So again, you could do long division or do tabular method 4 times, but that would be much faster if we knew the factor remainder theorem, right? Okay, next one. So write a polynomial in standard form with the following zeros. So the thing is, we have 3 zeros, so we know that we're going to need 3 factors. So if 2 is a 0, then x minus 2 is a factor. If 5 is a 0, then x minus 5 is a factor. If 1 is a 0, then x minus 1 is a factor. And it wants a polynomial, so this should be an equation. So you could do y equals, you could do f of x equals, whatever you want. This right here is in factored form, not standard form. Remember, standard form, we need it multiplied all the way out. So to multiply 3 things together, always imagine a simpler problem if you need to. Think if I was doing 2 times 3 times 5. First, you do 2 times 3 and get 6, and then you'd multiply that by 5, right? So it's the same thing we're going to do when we multiply polynomials. So I'm going to multiply these 2 together first. And it doesn't matter which 2, choose any. But this will give you x squared minus 7x plus 10. And then I'm going to multiply by x minus 1. You can use a table. You can use just distribution. So I'm going to do distribution on this one. So I'm going to do x squared times x squared times negative 1. So x cubed minus x squared. Negative 7x times x, which is negative 7x squared. And then plus 7x. And then plus 10x and minus 10. And then just combine your like terms. So x cubed minus 8x squared plus 17x minus 10. And remember, it's a polynomial, so you should have a y equals or an f of x equals. Very, very similar if we're dealing with imaginaries, right? Don't let this throw you off. It's a polynomial, so let's have a y equals. Negative 2 would be x plus 2. This would be x minus 5i and x plus 5i. So that would be my factored form. The key with multiplying these out is to always start with the ones that have i's first. You don't have to do it, but it's going to save you a lot of headache. Because when you multiply these out, you're going to wind up with x squared minus 25i squared. The middle terms will cancel out. and that's the same as x squared plus 25. Because remember, I squared is just equal to -1. So from there, now this is much easier to multiply because we don't have any i's, right? So we would have x cubed plus 2x squared plus 25x plus 50. And that would be in standard form. Now we can also go the other way. We can find the zeros. So if we knew the zeros, we could get the factors. If we know the factors, we can also get the zeros. So here's the factors. To get the zeros, we're just going to set each factor equal to 0. So this one would be x equals 0. This one would be x equals 1. This one would be x equals -2. And I know those have multiplicities. We could talk about that, right? This one has a multiplicity of 1. This one has a multiplicity of 1. This one has a multiplicity of 3 because that factor actually shows up 3 times, right? Now, if it's not in factored form, you're going to need to factor. So here, I see 4 terms. I'm going to start by taking out a GCF, see if that helps me. So all of these have an x. That leaves me with x cubed plus 5x squared plus 3x plus 15. Now, I still have 4 terms, so I'm going to factor this by grouping. So group the first 2. I can take out an x squared. Group the second 2, I can take out a 3. And that's going to give me the x that I had out front still. And then x squared plus 3 and x plus 5. So that's the factors. So let's find the zeros. So this would just be x equals 0. This one, x equals -5. This one's a little funny. We have to do x squared plus 3 equals 0, right? Move the 3 over and square root both sides. So this is x equals plus or minus I radical 3. So you have 1, 2, 3, 4 different zeros. Okay, and last one we're going to talk about this before we do some graphs is, okay, this says to divide this by x plus 4 and use that to find all the zeros. So I'm going to do tabular method, but again, you could do long division if you preferred it. So x plus 4 is going to go on the outside. In the box, I'm going to start with my highest degree, which is x cubed. So x squared would multiply to give me x cubed. This would be 4x squared. And I know these need to add to be 3x squared, so this would be -x squared, right? And then from there, this would have to multiply to be -x. This would be -4x, right? And that is going to need to combine with the diagonal to be -10x. So this is going to be -6x. So this would be -6. This would be -24. And that is what we want there. So that winds up being 0. So that tells me that x plus 4 is a factor, right? X plus 4 is a factor because my remainder is 0. Now, the other part of this is our quotient, right? So we can factor that. What adds to be -1 multiplies to be -6. So x minus 3, x plus 2. And now we have all 3 factors. So our zeros would be -4, 3, and -2. Someone just texted me that the chat is set to followers only. That is intentional. If you have a question, shoot it to me on Remind. You are welcome to do that at any time. But otherwise, the chat on Twitch is kind of unregulated. So it is meant to be that way. Okay, so we're going to start talking about graphs. If you have questions, send them on Remind again. Same thing. But we're going to do some graphing and then we'll wrap it up. So, end behavior. Remember our dances that we did, right? So, if we have an even degree, your hands should be even with each other, right? Even degree, hands should be even. If it's positive, it's up. Negative, it's down, okay? If you have an odd degree, then your hands should look odd from each other. They should look opposite. And I might be backwards from you, but if you have an odd degree with a positive slope or a positive leading coefficient, it should look like a positive slope. So I think that's positive to you guys right now. And if you have a odd degree with a negative leading coefficient, you would have a negative slope, which I think to you guys should look like that. But the idea would be positive slope is going to look like it's going uphill. Negative slope would look like it's going downhill, right? So those are important rules to know because those are going to be important when we actually do some graphing. So let's start with this one. Which graph has the following characteristics? 3 real zeros. So that means we should have 3 either spots where it hits the axis or a multiplicity of 2 at one of them, okay? And this also tells me that it's odd. So I'm going to go through and eliminate any that have even end behavior. Odd means you should have opposites, right? So I can cross out this one and I can cross out that one because those end behaviors match. And then this says as x goes to negative infinity, and remember on your x-axis, negative infinity is going to the left. The y value will go down. So what this means is on the left, this should go down. On the right, it should go up. So the only one that does that is choice 3. The other thing is being able to identify it from a function. So we're going to do a couple of these. We did a bunch of these in class today, but send me questions if you have them. So if I look at this first one, I look at my degree, it's a 3. So I see that that's odd, which tells me my hands should be odd from each other, right? And it's a positive leading coefficient, so it should look like a line with a positive slope. That line looks like this, so that means my end behavior on the left would go down, on the right would go up. For this one, right, I have an odd degree, but I have a negative leading coefficient. So odd, they shouldn't be odd from each other. Negative, it should be a negative, like a line with a negative slope. So this would be up to the left, down to the right. For one like this one, number 12, I have an even degree and a positive leading coefficient. Even, your hands should be even with each other. Positive, they should be going up. So this would be up on the left, up on the right. And let's say we had one like this one. So I've got negative x to the 4th plus 1. I have a positive or a negative leading coefficient and an even degree. And so even, your hands should be even. And then negative, they should both be going down. I would love to play Call Me maybe in the bathroom, but I don't want to get copyright infringement on YouTube. Okay, so graphs of polynomials. Let's talk about these. So the big thing on this that we need to remember is multiplicities, right? If you have something that crosses, I want you to remember that you could make that into an O, which would be odd, right? So cross, think odd. If you have something that touches, then I want you to remember that you could make that into an E for even, right? And that's going to tell you whether it crosses or touches. The other thing I would think is look at the way it crosses, right? So there it just straight up crosses. That is a multiplicity of 1. Here it crosses, but it flattens out. The more it flattens out, the higher your multiplicity is. So this is odd, but it has a multiplicity of 3. So let's do a couple of these. So let's look at this first one. I always start with my end behavior when I'm actually graphing. So from the graph, I see 3 factors. So I'm going to have 3 x-intercepts. So my x-intercepts are going to be at x equals 1 from this, x equals negative 2, and x equals negative 4. Okay? And let's think about our end behavior. So I've got 1, 2, 3 factors. They're all to the first power, right? And so if I multiplied those all out, my degree would be 3. And there's no negative in front, so the leading coefficient is positive. So this should go up on the right, down on the left. And since the multiplicity of each of those factors was 1, I'm just going to cross, cross, cross. So again, this is a sketch. It's not going to be perfect, but it should look something like that. Okay, let's look at the next one. So on this one, let's start with our end behavior. So the 1/12 does not have an x in it. That's not going to count towards my degree. This one is x to the second. This one is x to the first. So this is also a degree of 3. And there's no negative out front, so the leading coefficient is positive. So this is going to have the same kind of end behavior as the last one. It's going to go down to the left, up to the right. Now, I have 2 factors with an x, so it's going to look like it crosses, or it hits twice. So this is going to hit at -2 and at +3. Notice at -2, my multiplicity is 2, which is even, so it's going to touch there. And at 3, my multiplicity is 1, which is odd, so it's going to cross. So this should go up, touch, turn back, and then cross at 3. Now, on one like this, we're not given this in factored form, which actually makes the degree and leading coefficient part easier. So the degree here, you're looking for your highest exponent. Your degree is going to be a 4, and your leading coefficient is positive because it's positive out front. So 4 is even, so this will go up, up. Now, to get the zeros, we're going to have to factor this. So I'm going to start by taking out a GCF. And then factor what's left there. So x minus 3, x plus 1. So I have zeros at 0, at 3, and at -1, right? Now, let's check our multiplicities. At 0, we have a multiplicity of 2. That means it's going to just touch. Here we have a multiplicity of 1. It's going to cross. Multiplicity of 1, it's going to cross. So that would give me cross, touch, cross. Right? These should be smooth. They should never be pointy. So sometimes I just trace over it to make sure it's smooth. Okay, last one of these we're going to do, and then I want to do one where we work backwards because for some people that's harder. So looking at this one, let's start with our leading coefficient and end behavior. I notice out front that I have a -2, and so my leading coefficient is going to be negative. And then let's look at our degree. So I've got x squared, x to the 4th, x to the 5th. So the degree here is going to be 5 because we're multiplying these, so we're going to add our exponents. And so if it's negative and odd, I know it's going to go up on the left, down on the right. Now our zeros, this would be 1 at 0. This would be 1 at 5. This would be 1 at -3. And the multiplicity of this one is 2. Multiplicity of this one is 2. Multiplicity of that one is 1. So it is going to cross at -3 and then touch at the other 2. So here's what this should do. It should cross here, and then it's going to touch and come down like that. Okay, let's do one where we go the other way. So I'm going to scroll down. I'll come back to this. Let me add a page here. Add page. Okay, so I want to sketch one and then work backwards. We did a bunch of these in class today, but I want to make sure you guys feel okay about this. So let's say I gave you this graph, right? And I told you that we had 0 at -3, at 0, and at 2. And then what we saw that this went, make it a little thicker. So this went like this. Okay, so looking at that, I see that I have some end behavior to deal with. I have some other stuff to deal with. So what I always tell my classes is to start with the zeros, okay? If you have 3 zeros, that means you need 3 factors. And then we can mess with the multiplicities. So this first factor will be x plus 3. This middle one would be just x, or you could do x minus 0. This one would be x minus 2. So I know that those are all going to be factors. Okay? I know those are going to be factors. Then I need to think about the multiplicities. So let's go through. Okay, here this crosses, that touches, that crosses. So I'm just going to kind of fill out what we said before. Cross will be odd. Touch will be even. So the even one, I'm going to make that a squared. And then notice that these two that cross, they cross differently, right? This one on the right, just like straight crosses. That's going to be to the first power. This one on the left crosses, but it flattens out. That's going to be to the third power. Still odd, but just the next power up. Now, the last thing that we need to think about is the end behavior. This goes down, down, so I want a negative out front. And so make sure you have like a y equals or p of x equals whatever, but this would be your function. So start with your zeros, find your multiplicities, check your end behavior. It's sort of the opposite of what we do when we graph. Okay, one last thing I want to clarify if you guys are not sending other questions. There is a difference between symmetry and the degree, right? The degree tells me about the end behavior, up, down, up, whatever. Symmetry is something different. So we have talked about even and odd symmetry all year. If I talk about the symmetry of something, I'm talking about what it's like reflected over, right? So if we have symmetry over the y-axis, that is an even function. That is not necessarily the same as having an even degree, right? You can have something with an even degree, like this has an even degree, but that is not symmetric over the y-axis, so that is not an even function, right? Even degree is different than having an even symmetry, okay? For the odd, remember odd means you could spin it 180, or it'd be symmetric about the origin, and it would look the same. Now, this, again, is different than having odd end behavior, right? That green function has odd end behavior, but it does not have odd symmetry. I will do another working backwards problem after we finish this. Okay, so just hang tight. So keep that in mind. If I ask you about symmetry, you should be talking about what it's symmetric over, not the end behavior. Those are different, right? So like if I look at this one, is this symmetric about the y-axis? No. Is it symmetric about the origin? Yeah, if you spun this upside down, if I actually took this and like spun it, it would be symmetric, right? And so because of that, this is an odd function. It has odd symmetry, not because of the end behavior, because the symmetry is odd. Does that make sense? I'm asking you and you can't respond to me. You could like send me a remind, but that's all I got. So same thing for this one. If you look at the end behavior, we see that that has like odd end behavior, right? But that's talking about the degree. I'm asking about the symmetry. This is not something that if you rotate it at 180 would look the same, right? It would look different. So this is neither because it's not symmetric. This is what we've been doing all year. It's not the same as end behavior, right? Same thing with 3. Yes, this has an even degree because it has up, end behavior. But this function is even because it's symmetric over the y-axis, right? It's even over the y-axis. This function here is odd because if you spun it upside down, it would look the same, okay? So one thing I just want you to be clear on the difference between symmetry and end behavior. We've been doing symmetry all year. End behavior is very specific. Okay, let me do another working backwards problem, and then if you guys have more questions, just shoot them my way via remind. I'm happy to answer them. So let's say we have this, and we've got those points, and my function looks like this, okay? So looking at that, let me make it a little smaller so it all fits on the screen. I'm going to start with always, where are the zeros of this? Okay. So my zeros here are at -3 and at 1. I have 2 zeros. So in my mind, that tells me I should have 2 factors. So x plus 3 and then x minus 1. So that's what I'm starting with. I know these are my zeros. So then I know the factors, right? Now from there, let's think about multiplicities. So this one touches, that one crosses. So if it touches, remember that means my multiplicity is even. So I'm going to give that an even exponent. If it crosses, that means it's odd. So I'm going to say that's to the first because this goes straight through, right? It doesn't like flatten as it goes up. And then look at your end behavior. If you are looking like your line has a positive slope, right? Then that is going to be positive end behavior. So you don't need to put a negative out front. I will do one more like this. And if you guys still have questions, shoot them to me. So let's say we have this. We've got our X and Y axis. We've got this. Okay. And let's say that's at -2 and this is at 5, right? So if I look at this, I see 2 zeros. So that tells me I need to have 2 factors here, right? And let's think about multiplicities. So here this touches, that crosses. So touch, that's going to be an even multiplicity. So I'm going to make that squared. Cross, that's going to be an odd multiplicity. But notice that this like flattens out. So it's not just a 1. So I'm going to say that's a 3. The next odd number basically. And then look at your end behavior. It is looking like a line with a negative slope, right? It goes up to the left, down to the right. So you're going to need a negative out front. And so this would be y equals that with a negative there. Okay. So I'm going to hang out for like 3 or 4 more minutes. If you guys have other questions, let me know. Do your review sheet. Make sure you can, solve a quadratic, find a vertex. But this is really the new stuff. If you have questions on that other stuff, go back to my Unit 2 live stream. Look at that. You will be given the quadratic formula. That's not old, or that's not something you're going to need to know. So just go. Someone just asked, the highest multiplicity we will need to put is 3, right? We don't need to go higher than that. You really won't need to. In pre-calc, you'll talk more about that. But the idea would be like, let's say that you had a function where it was like that and then like that. You see how this one's flatter for a shorter amount of time? That one's flatter for a longer amount of time. This might be a 3, that might be a 5, but you're not going to really need to know that. If you know 1, 2, 3, I would say you're in pretty good shape. Those are the ones we practice in class. Those are what I'll test you on. Anything else, guys? Final countdown. I hope that this quality was okay. Twitch, I think, is much better than YouTube for not being laggy. Are flat lines going to be easy to spot on the graphs? Yes, the flat lines will be obvious on the graphs. So the basic difference you're going to look for is like, okay, if it straight up crosses, that's a multiplicity of 1. If it crosses in any other way, think about it as flat, right? If it does this, see how that crosses, but it flattens out a little bit, it'll be clear to you that it's doing that. You guys have good questions tonight. Can I draw something cool? Yeah, this is the only thing I know how to draw. Ready? Can you guess what it is yet? It's a giraffe. You're all welcome. If I ever become a children's book illustrator, it will have to be a book about a giraffe because it's the only thing I know how to draw. And I can only draw his neck. I can't actually draw his body. All right, last second. Yeah, you doubted me. I can draw a giraffe, man. Come on, world famous giraffe. can also draw a dog, but this one's not as impressive. Give him cute little hairs. There you go. That's all I got. Okay, guys, great questions. Nice job. I think this is going to be a great test. It is a 40-minute test. It's short. And yeah, send me questions as you're studying. I will see you guys later.